have discussed about the beta, the gain, and this is the IC. And when IC is small, the beta is controlled by recombination in the space charge region, and then at the moderate emitter current, collector current, this beta has to be rolled off by the turns numbers, alpha and gamma, and then at very high emitter current. Now this is the thing that we are going to discuss today, which is high level effects. Okay, so today we are going to discuss about the beta roll-off, increase in beta when the collector current is high level collector current. High level effects on beta. The first thing is high level injection. High level injection at emitter. And we are going to discuss about the high level injection at collector. And this has been known as Kirk effect. Okay. And the number 3 is going to be the base resistance. Obviously, the base resistance has a great influence on the device characteristic, especially when the current level is high, right? So the high level injection at the emitter, we have emitter, base, collector, okay? And if electron injection into the base by the forward biasing between this emitter and a base, then in the base, low level assumption that we had made for the base is no longer valid, okay? In other words, this is the low level injection case. We assume that the injected electron is less than the base doping. But if you have a high level injection into the base, then the base charge is not only the space charge region, the dopant concentration, but also this injected electron has a significant, it takes a significant portion of the total charge, like this. So in this case, the injection injection current should be proportional to the E to the Q VE over 2 VT, thermal voltage. Okay, that's what we have seen for the recombination, space charge recombination effect, right? This 2. This 2 means we have some roll off, the decrease in the beta. Okay, so this means beta is going to go down because of this at high collector current. Now for the if you have a high current levels at the collector at high current levels, our assumption of complete depletion in CB, space charge, region as no longer valid. Complete depletion in the space charge. So this happens emitter base collector. The electron is injected across this space charge region and it's going to be injected into the collector, and if electrons are traveling at velocity v, then the density is going to be simply, it's going to be shown like this at depletion. Right. So this Kirk effect we have the concentration profile is going to look like this. It's emitter, base, collector. So collector, the doping concentration of the collector is less than base and very much less than emitter doping concentration. Which means the depletion region in the collector is going to be extended far to the end of the device, while the depletion of the base into the base is going to be relatively smaller than the depletion region in this collector. Of course, in the emitter, the depletion region is very small comparing to the base, something like this. So space charge region is inversely proportional to the doping concentration, and the collector has the widest depletion region. So when this charge in the depletion region is significant in the collector because the doping level is very small. If the injected charges is comparable to or greater than Nx, the doping level, then this Kirk effect is going to be becomes significant. Means change in charge density in the depletion region, which is going to widen the depletion region. Into N minus collector. So the depletion region is going to be widened, which makes the beta goes down. Okay, at high current. And the details of this can be found in the literature. I'm just going to give you the brief idea of what happens in the collector and the base when we have a high current, and what's the effect on the beta, the gain of the transistors. Now, thirdly, we have to think about the base resistance. Actually, what you can immediately see that the collector current, we know this is proportional to the VBE over VT, right? VT from our voltage. That's the equation that we have when we ignore the base current. But if you have a significant or significant resistance of the base, or you have a very high current, then actually this voltage that we apply between the base and an emitter, it has to be changed to some values, VBE minus IBRB. That is the IR drop, as a matter of fact, IR drop. The IR is the voltage, right? So if you have a resistance of the base, and then the voltage that we apply between the emitter and base is going to be decreased by the amount of this. So the equation has to be changed to this. So this means if you plot the IC over VBE, of course it's a log scale, then you're supposed to have a straight line here, right? You're supposed to have a straight line, so something like this, according to this equation, okay? But if you increase the emitter voltage, then at the end it's going to be deviated from this ideal line, and this decrease in the current, collector current, is is because of the base resistance. Deviation owing to resistance. So we again have a low decrease in the beta gain at high current. So these are three facts are going to influence the transistor functions, especially the gain at the high currents. And in practice, the resistance, base resistance, we have to keep the base dopant concentration as low as possible to have a high beta, right? The gamma number. It is related to the gamma number. We want to keep this gamma number as small as possible to get a high current of the collector. But if you decrease the base resistance, then again we are going to have a high resistance value for the base, and at the high current is going to be, the beta is going to be decreased. In practice, this resistance, base resistance, and the Kirk effect, the collector space charge region, widening of the collector space charge region by the high current, those two factors affect. Those two effects are dominant on the device functions. So we have to optimize the doping level of the base and the collector. Well, there sum up the functions we have discussed about the beta. In terms of the beta, we have discussed at small current and intermediate current levels, and those three factors are related to the high level current. So that's about the operational functions of the bipolar transistors. Next, we have to think about the model, ever more model. We know that emitter current is going to be QA, the area, and diffusion coefficient, and base region, the gamma number actually, and it's the VO3T minus 1 minus it to the free CE over free T minus 1. Okay, that is the whole equation, and we can make the equation for the holes to be injected to the emitter. It's going to be at the same story. We can have a similar equation for that, which is going to be ND. Now we have forward bias of this. VE over T minus 1. Okay. We just only have one forward bias terms here. So in total current, it should be added because the polarity is opposite. So the total emitter current is the sum of this and IPE over INE. And then we can simplify this A11 e to the VBE over VT minus 1 plus A12 e to the VC over VT minus 1. This minus sign is we define the current flow into the emitter as a positive, so that we had just a minus sign for here for the correct current directions. Q A Ni square dN over NAXB dP over NDEXE, and A12 is KDN Ni square over NAXB. Similarly, we can have the collector current as A21 e to the VE over VT minus 1 plus A22 e to the VCB over VT minus 1. Here A21 is QADN and I scale over NAXB A22 is QA and I scale DN over NAXB DP NDC PC. Okay. That's just for the collector. The sign for the collectors. Okay. Usually A12 is equal to A21 in practice. And we manipulate these equations, and then we end up with some simplified form, like emitter current now can be written as forward bias current plus alpha R IR, and the collector current is going to be alpha F IF minus IR. And then we have 2, which is alpha R IR IF is IES Q IF. It's the VE over VT minus 1 of F IL. Okay, and I have base IV here, and here IR is ICS. And this is called, say, ever more transistor model. Here the alpha F is a forward gain. And that is IC over IE when VA is positive, forward bias. And alpha R is reverse gain, and IE over IC when CB is positive, and RES emitter reverse saturation current. ICS is collector. Let me give you one example. We forward bias base emitter junction and reverse bias collector base junction. That's active mode, as a matter of fact, right? That's what we usually call normal mode, say. Normal mode of operation of the bipolar transistor. Then IR is going to be 0, and the module reduced to so base current is going to be 1 minus alpha F. So this ever more model, it's good to find the current, terminal current, IC, IE, and IB. Okay, you can use this model to find those values. I think we have to, on Wednesday we are going to go back to this models again to have more, we want to put more physical senses on this charge control models. Ever more transistor model is just a simplified form, and then it is kind of thing that can be used as a tool to be used for finding to find the terminal currents. But we have to look into the physical mechanisms on the bipolar transistors in more detail in terms of the charges. Okay, to understand the physics, what's going on the bipolar transistors, and that will be done on the next Wednesday. Before that, we're going to discuss about the frequency limitations briefly. To sum up this today's lecture, let's see. Frequency limitations. If you use the bipolar transistors, and then if you want to use it at high frequencies, then the stored charges in the base actually is going to be is going to give us the limitations on the frequencies that we are going to use as an input. The injected charges and stored, and so therefore stored charges. Now, the first, what we have to think is the base transit time. We know in the emitter-based collector, and if you have a space charge regions like this, then we know that the charges in dopant profile is going to, that is MP naught, and that is almost a zero. Okay, so actually this thing is the injected charges in the base. Okay, so QB is nothing but QN PXB AE, emitter area. Okay, and transit time across the base is simply, it can be defined as the QB over IC, the current. Okay, that is the transit time. And then there's a transit time can be written as dn. Okay. Here, dn is average electron diffusion constant in the base. Now that is not that difficult to deduce that equation. Okay. Example. If XB is 1 micron and electron diffusion coefficient in the base is about 38 centimeters squared per sec, then the transit time in the base comes to 132 picosecond. Now, if the base is graded, the doping in the base, as we have seen in the base, is a doping is graded. You cannot make the base region doping constant. So if the doping is graded, we have a built-in electric field here, and then this built-in electric field will aid. That's a transit time, which means tau b is going to be reduced by at least 2 times. That's good. And if you have a high level injection, okay, then the whole concentration in the base will increase. Whole concentration in the base will be increased to maintain the charge neutrality in the base, right? And then this has a same effect to graded concentration in the base. So it is going to help to reduce the speed of electrons, and transit time is going to be decreased. So because of this and this and the basic fact, this base transit time is not dominant factor to limit the frequencies of in modern bipolar transistors. The frequency limitations, we can think of emitter capacitance, charging time. And in this, what we are going to think is the emitter and base in a space charge region we're going to think two factors in here. One is the junction resistance, RE, junction resistance, and the other is depletion capacitance. And that is depletion capacitance. So, as we discussed on the diode, this resistance is voltage divided by the current, and then that is Vt and IE. I think it's 1 over IE. Okay. And the rough estimate CTE, the capacitance is 4 times than CVE, where I think it should. This going to be over IE. It should on the denominator to follow that. Okay. Lastly, we can think about the collector capacitance, charging time. And here the emitter, base, and the collector, we are going to have space charge region and the emitter and base. And now here we are going to think about the capacitance and the resistance in the collector. The base collector junction is reverse biased. So the junction impedance is very high. Should be very high, right? It's high. And transit time is RCCTC. It's just simply RC delay thing, you know, the time is the unit that we can have when you multiply the resistance and the capacitance. And finally, we have one more thing here, which is a collector depletion layer transit time. Collector depletion and CV collector base is the reverse biased. And electric field across the depletion region should be very high. Okay, so that the electron should move at the saturation velocity. So for this, the depletion transit time now is going to be XD over free set. So as a whole, the transistor is going to be, the frequency is going to be limited by all of these factors. Our transit time total now is going to be sum of base, emitter, and collector, and then collector depletion region, so that the sort of cut off frequency of the device is now it's limited by these equations. And this is the frequencies when we get the beta is become to 1, and the device is no longer used as an amplifier. No longer amplification is possible. That's the limit of the frequencies that we can use for the bipolar transistors. And the typical number is the frequency is 500 megahertz to some gigahertz in the modern bipolar transistors. Okay. On Wednesday, we want to go back to the charge control model of the bipolar transistors, and then finally we're going to discuss about the scaling of the bipolar transistors, how we can make it small, just like the MOS transistors. Okay, I'll see you on Wednesday then.